In this video, we're going to do a breakdown of two volume problems using double integrals. For the first one, we're going to use rectangular coordinates, and in the second one, we're also going to talk about how to convert to cylindrical coordinates to find a volume. Our first example says use a double integral to find the volume of the solid in the first octant bounded by the coordinate planes and the surface z equals 1 minus y minus x squared. Because this is telling us to stay in the first octant and stay bounded by the coordinate planes, what that means is that we want x, y, and z to all stay positive, all stay greater than or equal to 0. So the lowest we're ever going to go is 0. And that's going to be our lower bound on all three axes. It might seem kind of difficult to do this without knowing what that graph looks like, but I do know that when x and y are 0, z is equal to 1, which is above the z equals 0 axis. So I know that this is my top bound, and then z equals 0 will be my bottom bound. When we set up a multiple integral, each individual integration represents a dimension, and then also our integrand represents a dimension. So if we're going to do two integrals with an integrand, we have a total of 3 dimensions in this problem, which means what we're calculating is volume. The bounds for your z-axis, f of xy is the same as z, are going to go into the integrand, and then the bounds for your x and y axes are going to go as bounds on your integrals. So our integrand here, from Calculus 2, we can insert the expression top function minus bottom function. We said this was going to be our top function, and then z equals 0 is going to be our bottom function. So if we subtract 0, it's not going to do anything. So really, we're just going to be using 1 minus y minus x squared as our integrand. When we decide the bounds for the double integrals, I typically use the order dy first and dx second. Multiple integrals are not calculated from left to right. They're calculated from inside out. So this innermost integral symbol goes with the dy, which means we need to know what are the bounds on the y function, or the y value. So to figure that out, we first need to look at what's happening in the xy plane. And that's when z equals 0. We were asked to use the coordinate planes as bounds. So in the xy plane, we don't need to consider z anymore because z is considered in the integrand. To figure out what's going on in the xy plane, we let z equals 0 in the equation for our surface. So we would have 0 equals 1 minus y minus x squared. And if we solve that for y by adding it over, we have y equals 1 minus x squared. Well, we were told to use y equals 0 as the lower bound, and what we've just found here is our upper bound. So now we've got the integral from 0 to 1 minus x squared of 1 minus y minus x squared dy. This is a double integral. There's also going to be a dx. So we need to know for that outer integral, what is the upper bound of x and what is the lower bound of x. So we keep working off of the last equation we have, which is y equals 1 minus x squared, and we're going to see what happens when y equals 0. That'll let us know what are the bounds on the x-axis. So if y is 0, we get 0 equals 1 minus x squared, And we're going to solve that for x. So x squared equals 1, which means x equals positive and negative 1. We were asked to stay in the first octant, which means don't go below 0. So we're going to ignore the negative 1 part and just use the positive 1 part. And now we have our bounds for the x, 0 to 1. Our bounds for our y, 0 to 1 minus x squared. And then the z function is the function we want to integrate. And we're going to start by integrating with respect to y first. When you integrate, you only want to consider that variable there in the problem. Anything else you see in the problem is going to be a constant, and you integrate it like it's a constant. So the antiderivative of 1 with respect to y is y. The antiderivative of y, we're going to do the power rule, and we get 1/2 y squared. And then the antiderivative for x squared in terms of y, x squared is a constant. So to integrate a constant, we just tack on a variable. And this needs to be evaluated from 0 to 1 minus x squared, which means we need to plug 1 minus x squared in for each of those y's, and then plug 0 in for each of the y's, and subtract the two results. When we plug 0 in, we're just going to get 0 minus 0 minus 0. So plugging 0 in is going to give us 0, and subtracting 0 does nothing. So to go on to the next part of our problem, we really just have to plug in 1 minus x squared and get our new integrand simplified as much as possible to get us ready for one more round of integration. So let's start by plugging in the 1 minus x squared everywhere we see a y. We'll have 1 minus x squared minus 1/2 of 1 minus x squared squared minus x squared times 1 minus x squared. And since there's still another integration to do, this is going to be a lot easier if we were to simplify and combine like terms. So this piece right here is going to have to be FOILed, and then we'll have to distribute the negative 1/2, and then we also need to distribute the minus x squared here. So I'm going to start working on removing the parentheses. First, if I FOIL, I'm going to get 1 minus 2x squared plus x to the 4th. And if we distribute back here, we have minus x squared plus x to the 4th. And then one more distributing, and we'll be ready to combine some like terms. So that's going to give us a minus 1/2, a plus x squared, and a minus 1/2 x to the 4th. I'm going to combine like terms, and just to keep it nice and organized, I'll start with the biggest exponent. I've got a plus x to the 4th and a minus 1/2, leaves us with a positive 1/2. A minus x squared and plus x squared cancel out, but there's still one more. So we'll keep that additional minus x squared. And then we've got some constants. We've got 1 minus 1/2, which is a positive 1/2. And now we're down to just one more integration with respect to x. So we'll do the power rule on each of these. We'll get 1/10 x to the 5th minus 1/3 x cubed plus 1/2 x evaluated from 0 to 1. If we plug in 1, we're just going to get our coefficients, which are 1/10 minus 1/3 plus 1/2. If you plug in 0, you're just going to get 0 minus 0 plus 0. And we can change all those to 30ths. So 3/30ths minus 10/30ths plus 15/30ths. And we're left with 8/30ths for our volume. This next example is very similar in that we're trying to find the volume of a solid using a double integral. But because this second example has x squared plus y squared in it, it's going to be much easier to calculate this volume in polar or cylindrical coordinates. Anytime we see x squared plus y squared, that should be a hint that tells us maybe we should do this in polar/cylindrical. Polar and cylindrical are really the same thing. Technically, polar is in 2 dimensions, and it uses r and theta. Cylindrical is 3 dimensions. It uses r, theta, and z. If you don't have a picture of your solid, you can use the link under week number 13 on our Moodle page. I have posted a link to a free 3D plotter where you can just type in your equation and see what this graph looks like. So we've got 9 equals 9 and z equals x squared plus y squared. So there's z equals x squared plus y squared. And let's add another z, add to graph another function. This time we want it to be z equals 9. Right now, though, our graph doesn't go up to 9. So we need to change the range on our axes so that the z will go all the way up to 9. And I'm actually going to tell it to go to 10. So there's our paraboloid. Z equals 9. 9 is a flat plane all the way up here at 9. So when we set up our integrands, remember we want to do in the z direction, top minus bottom. So technically, by being able to see what this paraboloid looks like, I know that that z equals 9 is going to be my top boundary because it's all the way up here. And the paraboloid, z equals x squared plus y squared, is going to be the bottom boundary. So in my integrand, I'm going to have top minus bottom in the z direction. And in the z direction, the top is 9. And the bottom is z equals x squared plus y squared. Because we have x squared plus y squared, though, this is going to be a lot easier to do in polar or cylindrical coordinates. So we have to remember how to convert from rectangular to polar or cylindrical. But z is the same in both. Z equals z, whether it's z in rectangular or it's z in cylindrical. So there's nothing we need to do there. But the x's and y's need to be changed to r and theta. And one of our conversion formulas says that r squared is equal to x squared plus y squared. And that means I can go back to this equation right here and replace x squared plus y squared with r squared. So my top boundary is actually going to be, in polar coordinates, it's going to be r squared. And any time we convert an integral from rectangular to polar, we always include an additional factor of r in the integrand. When integrating using polar coordinates, we like to use the order dr d theta. Now, it's not a rule, but that's typically the easier way to do it. So we need to see what's happening when these intersect. That's going to give us our biggest cross section, and we're going to use that to help us decide the bounds on the x and the y, which we're going to convert to r and theta. So those two intersect when they're equal to each other. So we're going to have 9 equals x squared plus y squared. But what exactly is that? That's a circle of radius 3. So that means r is going to go from 0 to 3. And it's a full circle. So theta is going to go all the way around from 0 to 2 pi. We just have to do a little bit of simplifying here in the integrand, and then we'll be ready to integrate and evaluate. So let's go ahead and distribute that r. We get 9r minus r cubed. And we first want to integrate with respect to r. So do a couple of power rules here. We get 9 halves r squared minus 1/4 r to the 4th, which needs to be evaluated from 0 to 3. So if we plug in 3, we're going to get 81 halves minus 81 fourths. If we plug in 0, we get 0. So the final integration we need to do is from 0 to 2 pi of 81 fourths d theta. Well, that's just a constant, so the antiderivative is 81 fourths theta. And we need to evaluate at 2 pi and 0. But evaluating at 0 just gets us 0, so the answer is whatever we get when we plug in 2 pi. So 81 fourths times 2 pi is going to simplify to 81
pi over 2.
And that is our volume.